Hello everyone, welcome back. In this particular video, we're going to go over the sulfonation of benzene. This is another example of an electrophilic aromatic substitution reaction where benzene is sulfonated. So the sulfonation reaction is done using fuming sulfuric acid as the reagent. And the product that we get is benzene sulfonic acid. So sulfonic acid is this group, SO3H. So in terms of a Lewis structure, we are looking at a sulfur that is bonded to 3 oxygen atoms, and then one of them is a hydroxyl group. So that's the structure of benzene sulfonic acid. Like I said, the reagent that we use is fuming sulfuric acid. Now, fuming sulfuric acid contains sulfur trioxide. So sulfur trioxide is the electrophile for this particular reaction. So sulfur trioxide is a sulfur, has a sulfur atom that is bonded to 3 oxygen atoms. And we usually show the Lewis representation with the sulfur double bonded to 3 oxygen atoms. But we can draw some resonance forms here. In fact, several resonance forms are possible. We can show one of them where we have the sulfur double bonded to 2 oxygen atoms, and there is a single bond with the other oxygen atom. Now, this resonance form, particular resonance forms, shows the electrophilic nature of the sulfur because the sulfur now lands a positive charge on it. So this sulfur is electrophilic here. Okay. And as far as the sulfur trioxide molecule is concerned, this resonance form, although it is a charge separated form, so there is charge separation here, but even then, this is a better representation of the bonding in sulfur trioxide. And that's because if we examine, let's say, one of the double bonds, the sulfur oxygen double bonds in this molecule, the pi bond here, so of the double bonds, one of these bonds should be a sigma bond and the other one is a pi bond. That's how all double bonds are. So one of them is a sigma bond and the other one is a pi bond. The pi bond, which is the double bond, or which makes the double bond, is formed by the overlap of a sulfur p orbital with an oxygen p orbital. Now, this is similar to a carbon-carbon double bonds, because when we have a carbon-carbon double bond, then the pi bond in the carbon-carbon double bond is formed by the overlap of a carbon p orbital with another carbon's p orbital. But the way how this is different, the sulfur-oxygen double bond is different, is that in case of a carbon-carbon double bond, the 2 p orbitals that are used, they're both 2p orbitals. That means they belong to the second energy level. So they are of equivalent energy here. Whereas for the sulfur oxygen double bond, this pi bond is formed by the overlap of a sulfur's 3p orbital with an oxygen's 2p orbital. And because these p orbitals are from different energy levels, so we're looking at a sulfur p orbital, which is 3p in nature, overlapping with an oxygen's 2p orbital. So this p orbital here is 3p, and this one is 2p. And since these are from different energy levels, which means they have different sizes, the overlap between them is not very efficient. And so because of that, the sulfur-oxygen double bond is polarized. which means it is better represented with a single bond nature with formal charges on sulfur and oxygen. And what that means is the sulfur has a positive charge on it, formal positive charge, which means it is a very electrophilic center here. So that's why sulfur trioxide is a highly electrophilic species molecule. And so that serves as the electrophile here. So in terms of a mechanism for this particular reaction, the first step, like all other electrophilic aromatic substitutions, involves an initial attack by a pi bond in the benzene on the sulfur, because that's the electrophilic site here. And simultaneously, the pi bond here is going to move up to the oxygen atom. And so this would give us our sigma complex. And as we've seen before, since benzene is a symmetric molecule, it doesn't matter which pi bond we use. We can use either one of these pi bonds, like any of these three bonds, to attack the sulfur atom. So we've got the sulfur. Now the sulfur has a double bond, two double bonded oxygens, and then one oxygen which carries a negative charge. And there is a hydrogen here and a carbocation on the other carbon. So we've made our sigma complex essentially here. And this sigma complex, like other sigma complexes we've seen previously, this is resonance stabilized. And so essentially at this point, any base in the system, like water, which could be a solvent here, that can come and deprotonate this hydrogen, and electrons from that bond fall into the space to reform the pi bond, and so that the molecule is going to regain aromaticity. It will regain aromaticity now. And then from here, it have a final step where the oxygen here gets protonated, and it will give us the benzene sulfonic acid. So there we have it. That's the benzene sulfonic acid along with water. Okay, so that's the mechanism of the sulfonation of benzene. I hope everyone finds that video useful. Bye.